Welcome to this demonstration on the magnetic effects of electric current. In this video, we'll explore how a current-carrying copper wire generates magnetic flux and observe the fascinating interactions using compasses. Let's dive in and see the principles of electromagnetism in action. When we place compasses around a current-carrying conductor, we observe a fascinating behavior. Each compass needle aligns itself with the magnetic field created by the electric current flowing through the conductor. As the current flows through the copper wire, it generates a magnetic field that forms concentric circles around the wire. This field can be visualized using compasses placed at different points around the wire. If the current direction is reversed, the direction of the magnetic field also reverses, causing the compass needles to change their orientation accordingly. Each compass needle, which is essentially a small magnet, aligns itself tangentially to the magnetic field lines. This means the needles will point in a circular pattern around the wire. But what happens when we take this straight wire and coil it into multiple circular turns, forming an inductor? In an inductor, the magnetic fields generated by each turn of the wire combine, creating a much stronger and more concentrated magnetic field inside the coil. Each turn of the coil generates its own magnetic field due to the current flowing through it. These fields are represented by circular lines around the wire. We'll see the magnetic fields from individual turns of the conductor combined using vector addition. Vector A points in a direction that is 45 degrees below the horizontal. Vector B points in a direction that is 45 degrees above the horizontal. When we add these two vectors together, we get a resultant vector, which we will call vector A plus B. Notice that the directions of the vectors and their angles determine the direction and magnitude of the resultant vector. By visually placing vector A and vector B tip to tail, we can see how they combine to form vector A plus B. The resultant vector, A plus B, represents the combined effect of vector A and vector B. This is how vector addition works. It is a fundamental concept in physics and engineering, useful in understanding forces, velocities, and many other physical quantities. In some areas, the fields strengthen each other, while in others, they may partially cancel out. According to vector addition, the fields combine to form a resultant field. This means the individual magnetic fields add up at each point in space. When neighboring turns generate their magnetic fields, the fields interact. Inside the coil, the magnetic field lines are linear and parallel to the axis. Outside the coil, the field lines spread out and loop back to the other end of the coil. We see a DC voltage source connected to an inductor. As the voltage from the DC source increases, it causes a corresponding increase in the current flowing through the inductor. According to Faraday's law of electromagnetic induction, the increasing current generates a time-varying magnetic flux within the inductor. This changing magnetic flux is proportional to the current flowing through the coil. As we observe the inductor, notice how the magnetic field strength, represented by the density of the flux lines, increases with the current. This visual representation helps us understand the direct relationship between the current and the magnetic flux in the inductor. The magnetic field generated by the solenoid exerts a force on the nearby nails, causing them to be attracted to the electromagnet. Watch as we increase the DC voltage applied to the solenoid. This coil of wire, wound into a helix, is designed to produce a magnetic field when an electric current passes through it. We see the concept of magnetomotive force, or MMF, in the coil and the current, I, flowing through it. Mathematically, this is expressed as MMF equals Ni. The number of turns, N, refers to how many times the wire is wound around the core of the inductor. MMF is responsible for creating the magnetic flux within the inductor, illustrating how the number of coil turns and the current together determine the strength of the magnetic field. Hey there! If you enjoyed this video, make sure to give it a thumbs up and hit that subscribe button. Thanks for watching, and we'll see you in the next video.